All right. So what are we doing today?
It's kind of a follow-up from our discussion of Bell's theorem and Bell's inequality. We touched upon it a little bit as David Bohm and his take on quantum mechanics. So we wanted to go into more detail about Bohmian mechanics. And it was kind of an excuse for, I think, both of us to look into something that we are both interested in, but maybe haven't spent as much time as we should have kind of sinking our teeth into it.
Yeah, it's definitely like a theory that, I mean, from what I've read, it's been kind of revitalized starting in the 90s, but like in the last couple years, I feel like I've seen a lot of like pilot wave type, and like pop science. So it is something, that I did want to look more into.
Yeah, exactly. And I think talking about it a little bit before hitting record, I think we both found some books and looked into things a little bit online. At least I did. I don't know what you did online, but yeah, I got some stuff to talk about.
Yeah, I kind of read through a book, or at least the important parts of a book, looked up some stuff online, watched a few videos, and I can definitely say I am no Bohmian mechanic pilot wave expert at this point, but I think I have like a okay sense of some of the major differences between, kind of the standard Copenhagen interpretation and Bohmian mechanics.
Yeah, and maybe that's actually a good place to start, is talking about the fact that there are interpretations of quantum mechanics, like that those even exist, like that quantum mechanics isn't, set in stone as it exists. People are still trying to figure out what does it actually mean.
Yeah, so I've heard of like, at least 3 big ones, and I know there's even more than that. I think it's kind of an interesting thing that like kind of one of the key things I think for any interpretation of quantum mechanics, and like a thing to realize, is that in order for it to be like an interpretation of it, is it can't have like different predictions. So these aren't different, like all these theories, all these interpretations have the same predictive power, at least in their realm of applicability. But it's kind of like the ontology behind them is different. Like it has it describes a different reality.
Right. Yeah. And everyone agrees, everyone being physicists who study quantum mechanics all agree the outcome of experiments, quantum mechanics predicts those outcomes. And we see the predictions, seen through to the results of the experiment confirm what we know of quantum mechanics. The question is, what does it mean? and I think, we're all taught in school, the textbooks go through the Copenhagen interpretation, which I think David Merman was the one who coined the term "shut up and calculate" as the name for the Copenhagen interpretation, which I think really encapsulates what the interpretation means. It's like, don't worry too much about what it really means, but just do the calculations, trust the math, and you'll get the right answer. And that's really all that matters. That's kind of the Copenhagen interpretation. Yeah,
it has really high predictive power, really strong predictive power.
Right.
Where it agrees, like our experiments agree really well with theory. So, don't worry about what the underlying things that are happening behind there, behind the curtain. Just, we know how to calculate an outcome and start there.
Right. Yeah. I mean, Copenhagen is essentially, you have a wave function that describes the system. It evolves through time following Schrodinger's equation. And then what Schrodinger equation tells you is the odds of certain outcomes happening, essentially. So the way I like to describe it is thinking about horse racing. And if you've ever been to a horse race, like in person, or maybe followed one online, if you're betting or something like that, the odds for each horse are printed ahead of time, like in the newspaper, you can look them up, but they change over time leading up to the start of the race. And the odds are actually fluctuating based on who's betting on which horse. And so Schrodinger's equation is essentially telling you how those odds are going to change. And it is deterministic. Like you start with initial odds and you let the Schrodinger equation evolve the wave function, the odds over time. And then at the end, or at the start of the race, you're going to see what the odds were that Schrodinger equation told you. So those odds started at something, they changed to something else. Everything is completely agreed upon, understood in quantum mechanics. Schrodinger equation tells you how those odds change. The problem is the second you make a measurement, you're going to get an outcome of one of those horses that's going to win the race. That's where quantum mechanics and Copenhagen essentially falls flat. Is it can't tell you how to go from the odds of all the horses at the start of the race to one horse finishing. All you know are the odds, and then you end up with one winner.
Right. Yeah. It's almost like I feel like this is a fair add-on to this analogy, and you can correct me if you think otherwise. But it's almost like with the Copenhagen interpretation, it's like the one horse that finishes was like the only horse at the end of the race.
Right.
Like there weren't other horses now.
Yes. Yeah. Exactly. It's just, all of the horse race, reality of the horse race has collapsed, to use the technical word that we say, down into one horse. And that's the only horse that exists. And moving forward, if you made a measurement again, like which horse is there, there's still only going to be that one horse. Like the reality exists as that horse. But up until that race was run, we didn't know that all the horses existed.
Yeah, maybe. And this might be something that we can go in general deeper into, in terms of I think this might be an ongoing thing for us where we kind of look at different interpretations. And, we're going to start here with Bohmian mechanics, but we could also delve more into, the Copenhagen interpretation later, which is kind of, more of the standard thing, which I think is why we're not starting there. If you've had a quantum mechanics class, then that interpretation.
Right. Yeah. And a lot of times people say the problem with Copenhagen is the measurement problem. The act of measuring, you end up with one result at the end. Quantum mechanics has no way to tell you how that happened. Like, all it can tell you are the odds leading up to the measurement. And then after the measurement, it can tell you what happens. But the actual measurement, there is no explanation for it in Copenhagen. And I don't even, I was going to say, I don't know that there are answers in the other interpretations, but that's not totally true. I think that measurement problem is the hidden kind of issue that interpretations are trying to get at. They're trying to say, okay, let's do all the predictions that Copenhagen does, but then let's also try and explain that measurement, like what's happening there.
Yeah.
Why is there that gap in the Copenhagen interpretation?
Yeah. What's actually, going on here? Let's not just shut up and calculate. Let's try and I think the hard part though, is that you can't at least right now in history, and maybe this might not be true for all interpretations, but you can't differentiate between the two, any of the interpretations, at least Bohmian mechanics and Copenhagen, in terms of a measurement that you could perform right now.
That's right. Yeah, these are all, they all make the same predictions. Copenhagen interpretation of quantum mechanics makes, that the experimental results are all predicted to be the same in all of these interpretations. But one of the books that I checked out called The Ghost in the Atom, which has interviews by several different physicists about this topic. And one of them is Bohm. One of the physicists is Bohm himself. And the interviewer asks him, well, since you can't propose a measurement to or an experiment to test your interpretation, why should it be taken seriously? And he came back with, well, if that was the only requirement to have a viable scientific idea, then so many scientific ideas of the past would have been shot down before we even had an idea to think about them. Like no one would have heard of them. And he specifically went back, to Democritus bringing up the idea of the concept of an atom. And he's like, it took 2,000 years before we can get an experiment to show atoms exist. But the idea has been there for 2,000 years, and it's been, on people's minds, and people had been thinking about it since then. So it doesn't make it any less valid of a theory because we didn't have an experiment for it. We might not be able to, find an experiment right now that can tease out the difference between any two interpretations of quantum mechanics. But that's not to say that, if you follow that interpretation deep enough, at some point you will be able to say, oh, here's a difference between these two, and we can now test this. Yeah. Right. Yeah, we haven't gotten there yet, but the fact that all these interpretations are out there and competing, I think this is a really interesting field of physics. And I would think it's actually a little unfortunate that it's not, since it is kind of skating really close to philosophy, it's not taken seriously like super seriously. Like if your field of research was interpretations of quantum mechanics coming out of grad school, like you probably wouldn't be able to find an academic job very easily without doing something else. Like there's not that many quantum mechanics interpretation physicists out there that's all they do. You know, a lot of them do it on the side. A lot of them publish kind of weird papers out there, and someone discovers it decades later and says like, hey, this is kind of legit. We should probably pay attention to this. All the interpretation namesakes and people who came up with them have kind of been lost to obscurity and then looked back upon, and people realize the genius of their work.
As a quick aside, we won't delve into it in this podcast, but you know, the many worlds interpretation is probably I feel like the next biggest one after the Copenhagen interpretation, or maybe with Bohm. But exactly. The guy that I heard Sean Carroll speak, and he was talking about a guy that came up with that theory, Hugh Everett. Apparently, he got like laughed out of the field. Like they're like, this is just ludicrous what you're saying. Like, don't even, you know, why are you even bringing this up? Like we've already have it figured out, you know. And so, yeah, it is a little, you know, a little downside to physics. And that's actually like the book that I checked out. I didn't read that part of it, but it's by James T. Cushing, and it's just called, well, the full title is Quantum Mechanics, Historical Contingency and the Copenhagen Hegemony. Hegemony? How do you say?
Hegemony. Hegemony, either one. By the way, that's my wife's favorite word. All her students know that that's her favorite word.
Yeah, so in this book, he talks about the Copenhagen interpretation, and he talks about the Bohmian interpretation. And then the part that I didn't read that he kind of goes into is like, why did we pick one over the other? Because actually at the same time that they were coming up with the Copenhagen interpretation, De Broglie, I think is how you say his name, right? De Broglie. Let's see if Wikipedia can tell me. But anyways, he proposed this theory of pilot waves back in 1927 or something like that. And Everett, he got laughed at for his truth. I think like Pauli was one of the bigger dissenters of his theory, and that kind of put him. So he actually like turned and said, "Okay, I'm going to go with the Copenhagen interpretation." And then it just kind of sat. Pilot wave theory sat there doing nothing until Bohm picked it up in the 50s. But so he kind of talks about in this book, like, why is that the case? And like, could it have gone the other way? And like, what would that mean? I didn't read that part of it, at least yet. That's probably,
Yeah, there are a lot of books on this topic. One that I didn't check out was a collection of letters written between physicists, including Bohm and Einstein, and I think de Broglie was actually in there, and Paul Dirac. I don't know, a whole collection of physicists writing to each other about Bohmian mechanics, essentially, and the letters that they're exchanging of support of Bohm, who, if we get into the history, just to touch upon the history a little bit, is he had a position, I believe, at Princeton during the Red Scare and was called to testify against colleagues and to out basically communists within the academy. And he refused. He pled the fifth and said, no, I will not go. And because of that, he lost his position at Princeton and was not hired back, even though later on the courts found that pleading the fifth is completely legal. Like he did nothing wrong to do that. And obviously we look back on that as a terrible blemish on American history and the judicial blemish on American history. Yeah. And Bohm, I got another job, but he left for the United Kingdom and got a job in England as a professor. But yeah, he lost his work because of that. And Einstein wrote a letter in support of Bohm at the university in England as essentially a letter of reference from Einstein himself supporting Bohm.
That would be great to have in your
yeah.
resume.
I read it, and it was, Einstein was like, this guy does some amazing work. People don't realize how smart he is, but he's doing some great stuff. And actually, one of the books we'll talk about, I took the class from the author of the textbook, who was, when I took the class, the professor was very old and about to retire, but he had been at UC Santa Cruz for a long time, and they were hiring for a physics professor. And one of the physicists who did one of the few experiments that tested Bell's theorem, not aspect, but I think his name is Clausier. I forget his name. He applied for the position, I believe, and the department said, no, he's doing fringe experiments on, the nature of quantum mechanics. We don't want that type of work happening here. And my professor fought to get this guy here because he's like, this guy's brilliant. He's doing really important work testing quantum mechanics, but they thought it was too fringe and he didn't get the job.
Yeah. I mean, it also sounds like, one of the big things that you need to do as a research professor, especially at like a UC, is, you have to be able to publish papers, and this stuff it sounds like it's just not, it's probably not going to get published in like Scientific American or something. Actually, maybe Scientific American would be the one to publish it, but not like a standard physics.
Yeah. They did just come out with a new test of Bell's theorem that, one of the problems is the like inherent in randomness, like of random number generators is, how good can you really get a random number from a computer? And they came up with a new way actually with video games online and people across the world playing this video game. And basically the key clicks of the people playing the game were the inputs for the random number generator. And so they used this huge data set to pull actual randomness to start the experiment to get the initial conditions completely random. And that was just published, I think, in Nature pretty recently, within the last couple months.
That's pretty cool. Yeah, that's interesting.
Yeah. So I guess my point is that experiments do get published when I do think there's some sort of change happening recently to test these interpretations, or at least, test Bell's theorem, I guess. Yeah.
I definitely think it's like more accepted to talk about these things, which is why we're hearing about, Bohmian mechanics and the many worlds interpretation.
I did see when I was in grad school that they did a survey of physicists at a conference asking them which interpretation they felt aligned with or thought was, the way to go. And I think many worlds won out. And it definitely wasn't Copenhagen. And I'm pretty sure many worlds was the one that most people were leaning towards. And I remember talking to a grad student when I was in this class. This guy wasn't in the class, but I remember talking to him about taking the class. And he's like, well, isn't it just decoherence? Isn't that just the answer? And I was like, well, that's presented as one of the, competing interpretations. So yeah, you get taught these other interpretations and they kind of just chalk it up and say, well, that's the one, but we don't really know. There's lots of different viable options out there. So why don't we get into Bohmian mechanics? We haven't actually said what it is. Right. We've talked about Bohm, the person, and a few other interpretations. Right. But
yeah, I think that's a great idea. But 1 second. I just clicked it. I just needed to hear it on Wikipedia. De Broglie is how the computer says. Yeah, but
the Bears.
But De Broglie, apparently.
There's a clip of Feynman pronouncing it De Broglie. He's like, I'm a terrible American, and that's how I pronounce it. And I don't know. That's always stuck with me. But that is how I learned it, is De Broglie. But I know that's not right.
Wikipedia said De Broglie.
De Broglie. Yeah.
But I don't know a lick of French, so
yeah, same.
I'm going to go with whatever Wikipedia tells me it is. Mm-hmm. Someone just programmed it in like yesterday to make it say like, butthead or something. I have no idea.
Right.
But I'm going to trust Wikipedia. Yeah. Okay. Sorry for that side quest. Yeah. So, okay. What is Bohmian mechanics? What is the interpretation? Or pilot wave theory is another name for it.
Mm-hmm. So the way I understand it, the simple explanation I have, which I tried to find textbooks that were like, these are the equations, and the library just didn't have that. I don't know where those textbooks are. They must exist somewhere because I've seen the equations on talks on YouTube videos of people giving conference proceedings about it. And I've seen the equations.
They're at research libraries. I have one.
Oh, okay.
By Holland. It's called The Quantum Theory of Motion.
Okay. Cool. Yeah. So my San Diego Public Library did not have a textbook that had it, or at least I didn't find it. Maybe it's there somewhere, but I didn't see it. So the way I understand it is in Copenhagen, you have the Schrödinger equation, and that's it. It's Schrödinger equation and then measurement. And that's the whole story. In Bohmian mechanics, you still have Schrödinger's equation with the wave function, but there's an additional equation that essentially it represents the path that the particle takes, which is not given by the Schrödinger equation. The Schrödinger equation is a wave equation, and that wave function gives rise to a quantum potential or force that directs the actual particle's position and path in that second equation. and the two kind of feed into each other. So you have essentially a second equation added into quantum mechanics.
Yeah, a guiding equation is, I think, one of the ways that they refer to it. And it gives the velocity of the particle, I believe, but it's based on the wave function as well. So yeah, both of those things, essentially there is the wave function still, and then it evolves according to Schrodinger's equation. But then that, while it's evolving, it's also guiding a physical particle, in a certain direction through this quantum potential.
Right. So the pattern that's produced from the double slit experiment, for example, it's the wave function that exists between the source of the particle and the screen with detectors, showing where the particle hits the screen after passing through two slits. That wave does go through both slits. The particle itself doesn't. It just follows the crests and troughs, kind of bounces around the wave, being guided by the wave. And it does pass through one or the other slit, the actual particle, and then hits the screen following the pattern of the wave function that the wave function set up. So there's a particle that it's like meandering through these valleys inside the wave function.
Right. Yeah. So like I think I want to focus on the double slit experiment a little bit, where, we shine light. Let's start with Young's double slit with light, right? And you shine it through two slits and you get an interference pattern on the other side, provided it's coherent light and all that jazz. The sizes are right. And that could be strange. It could be normal, because we can treat light sometimes like a particle or a ray, and sometimes we can treat it like a wave. But then we say, okay, all right, let's do the same experiment, but we're going to do it with electrons, which I think, at the time of this being done, it's like, okay, an electron is a particle. That's what we know it as. That's what we think. And then when you do it with an electron, you get an interference pattern on the other side, which is that is really mind blowing. And so it's saying, okay, wait, an electron is a wave. It's a wave. And then that's where kind of, Copenhagen term says there's a wave function that's describing this electron, and that's it. But then Bohmian mechanics says, no, the electron is still there. There's also a wave function. Both of those things exist, and the wave function guides the electron.
Right. Yeah, that's the pilot wave. It's piloting the particle through the wave function, through space, through the experiment, through the apparatus, all of that. The wave function exists, and it's described essentially through Schrodinger's equation, as we know, as everyone who takes quantum mechanics in school understands. But there's just another equation that's showing the particle itself, how it's being forced by the wave function into these particular positions, locations, velocities.
And one reason this might just feel nice right off the bat is when you do the double slit experiment with an electron, when it goes through the slits, it interferes with itself, or if you're doing single electron, then it hits some screen on the other side, some detector, but it hits it as a point. It's not hitting all spaces of the detector at once. It's hitting, we're seeing it, the detector seeing it at a single point. So it feels like there's an electron there,
right?
Right. Like a particle.
The particle, exactly. The particle exists still.
Yeah. Which in the Copenhagen interpretation, this is where we say there's a collapse of the wave function to that point. But Bohm says, don't worry about that. It just hits it. Yeah. There's an electron there.
Yeah. We lose wave particle duality in Bohmian mechanics. There is the wave, which is something separate from the particle, and the wave is just guiding the particle through space.
And I think one slight important thing to point out is that Bohmian mechanics, everything we've said so far, is true of non-relativistic quantum mechanics. They're actually, we can talk about this later, but there isn't a relativistic version of Bohmian mechanics yet. There's an accepted one that I know of.
Yeah. I didn't know that. I didn't explicitly, I didn't hear that somewhere, but it makes sense. This is not relativistic. Something else to note is A place that this is demonstrated really well is a video by Veritasium. I don't know if you've seen it. It's I think it's called "Is This What Quantum Mechanics Looks Like?" is the title of the video, and it's I don't remember exactly what the fluids are, but let's say it's water on a speaker that's kind of being vibrated, like one of those standing wave plates kind of things, where you get these waves, these troughs and crests of water, and then there's a drop of oil that's dyed a different color, like black or something like that, that's bouncing around on the water waves. And he says, like, this is the particle, and the wave itself forms its shape, as we understand through Schrodinger's equation, and the particle itself is just guided by these waves across different situations. And they do the double slit experiment showing the wave function itself of the water waves, but then the oil drop bouncing along the water waves as it goes through the double slit pattern, like through the double slits, hits a wall on the other side.
Yeah, it's a really cool video. It kind of like is a good analogy of kind of like what Bohm is talking about.
Did he ever use the word Bohmian mechanics in the video? I remember watching it and thinking that's what he was talking about, but I don't remember him actually calling it out and saying that
he might have said pilot wave.
Pilot wave, okay.
But one of the key differences though between that and Bohmian mechanics is, in reality, that oil drop is bouncing on the water. And it is creating waves. It's interacting with the water itself. In Bohmian mechanics, the particle does not act on the wave function. Only the wave function acts on the particle.
The particle doesn't press on the wave function and make an indentation itself, like the oil drop on a water wave would. Right. Yep. So I think to tie this back into what we talked about with Bell's theorem is Bell's theorem said all quantum mechanics predicts all interpretations of quantum mechanics predict the results of the spin measurements on two different particles. And it has to go with the cosine of the angle between the detectors. And go listen to the last episode about Bell's theorem to find all the details of that. But there's a particular prediction that quantum mechanics makes, and that's regardless of the interpretation. All of quantum mechanics interpretations make that same prediction. And what Bell's theorem ruled out was quantum mechanics and local hidden variable theories being both correct. So you can't have quantum mechanics being correct and a local hidden variable theory of reality being correct.
Right. Now, I was going to say, as a quick summary or reminder, I think the way we described that last time was, when this particle decays into two other particles, one spin up and one spin down, or vice versa, they're in a superposition. It's Bohm said, let me imagine there's some hidden stamp that we can't see, is how we put it, on these particles that's labeling this as spin up or spin down. And if you make that assumption, then you end up with a inequality that can't be true based on experiment that we've done so far with quantum mechanics. So he's kind of ruling out that locally stamped on these particles ahead of time is a spin up or spin down sign.
Right. Bell. I think you said Bohm, but Bell.
Oh, sorry.
Bell
it was
that.
Bell.
Yes. Yeah. So exactly. These hidden stamps on these particles, they don't exist. They can't exist, and quantum mechanics also be true. But we've done tests, and it's one or the other, and the tests show that quantum mechanics is right. So that's Bell's theorem and Bell's inequality. No local hidden variables can exist with quantum mechanics. But we have space for non-local hidden variables. And I'll admit, I can kind of fudge an explanation of non-local hidden variables with Bohmian mechanics. Do you have a good one? Something you think is good that explains why Bohmian mechanics is considered a non-local hidden variable theory? Because I know it is, but I don't really know what about it makes it non-local hidden variable.
I don't know in a great detail. This was like one of the topics that they covered in the book that I read, but it was a little beyond me in the moment. But I think like the way I kind of got it is Bohmian mechanics is causal, meaning measuring one of the particles causes the other one to be the other way through a non-local instantaneous
interaction. Yeah. And I think what trips me up is thinking about the pilot wave theory with the double slit experiment. I got a great visual for that. Like my mind can grasp what that looks like and how that works. when we start doing Bohm's version of the EPR paradox or EPR experiment, Bohm's version being the two spins separated, two particles really far apart, and the spins are measured on each particle separately. There is a wave function that describes both those particles, and Bohmian mechanics shows the wave function existing across all of space between those particles, and they have a value at each position, at each location that the measurement happens for any position of the spin detector. And I don't have a great picture of that, but it's essentially the wave function would have to exist in a certain way that anytime the detector on one end measures up, if the detector is in the same position on the other side and measures the other particle, it's going to give it spin down. And somehow the wave function communicates, or it's not that it communicates. That's where I get tripped up, is there's not a signal being sent. It's that pilot wave has answers to all those questions ahead of time. And it's non-local because one detector's positioning, the answer for that is encoded at that place in space as it is at the other detector in the same position. The answer is also encoded there. And so it's like Bohmian mechanics does answer across all of space, given the initial conditions. It's just, it exists already. It's set up ready to give you the answers that you see in quantum mechanics. I think that's the non-local part.
Yeah. It's predictive to some level. In this case, this experiment, it's predictive. I think there is I'm not even going to try and venture a guess.
Yeah, that's what I'm kind of doing too, is like I can piece it together, but I don't have a great explanation as like Bell is non-local because of this. Like,
right. Well, maybe that's something we could focus on a future topic. But like I think one of the key things though to note with Bohmian mechanics, I mean, I don't think this necessarily is like ruled out in the Copenhagen interpretation, but you don't really talk about it, is in Bohmian mechanics, there's a wave function of the universe.
Right.
Like it's not just like your electron or your two particles or whatever. The whole universe is involved. And you have to take that into account.
Right. Yep. In Googling and looking stuff up online, did you ever come across a YouTube channel called Looking Glass Universe?
That sounds familiar. That might have been one of the earlier videos that I watched.
It's a female narrator who's, I think, Australian. Apologies if it's New Zealand. I'm not sure. But she has a series of videos talking about Bohmian mechanics, and they're pretty good. And she brings up something I hadn't seen in any of the books I read, something called contextuality. Did you see that anywhere?
I don't think so.
Yeah. So she highlights a problem in Bohmian mechanics, a problem in the sense that it sounds like it shouldn't be right, but it doesn't. It's not a problem in that it makes a wrong prediction. All the predictions are still correct. It just feels wrong. So the contextuality is, if you measure spin up, you would expect that the particle was spin up no matter how you measured it. Like if you measured our height, like, which is some aspect of reality for us. If I measured my height, I would get the same answer if I used a certain, if I used a ruler and stacked it a bunch of times, if I did it well enough, and if I used a tape measure, and if you use some like laser, sighting range distance reader, right? Like right. I should get the same answer for my height, no matter how I measure it.
Right.
But Bohmian mechanics has a problem where that if you measure spin up, when you measure it a particular way, you could get spin down if you measure the same particle in a different way.
Oh, that's interesting. I don't think I ran across that.
Like set up the experiment, run your experiment, you'll get spin up. Set up a different experiment, but it's the same initial conditions, you're going to measure spin down.
Huh.
And it's a particular problem with spin, not velocity or momentum or mass or things like that, but it's a spin problem.
Yeah, that was one thing I like. Most of the stuff that I looked at all just said, okay, like we're gonna talk about spinless particles, or like pretend particles aren't, like the spin isn't involved in this measurement. I didn't get too deep into anything to do with spin in Bohmian mechanics.
Yeah,
but that's really interesting.
Yeah, I hadn't heard that, but apparently is an issue with Bohmian mechanics. But it's still, I mean, the measuring of spin up or spin down, it's still a probabilistic up or down thing. So you still get up and down 50% of the time if it's a sideways spinning particle in the setup of the experiment. So you still get the same predictions, you still get the same results that you would predict, but it's just has the problem that if you analyze it, absent of the experiment, but you do the physics, if you measure it a different way in your theoretical experiment, you would get an upside down answer if you did the experiment a different way, which should give you in Copenhagen, it should give you the same answer. So there is a contradiction there.
I almost wonder if you could tease that out by doing repeated measurements on the same particle.
Yeah, it made it sound like it wasn't something that was testable, but it was a prediction. Like it was something you could see on pencil and paper, but not in an actual experiment.
Yeah, it sounds like it wouldn't be a testable thing if it's really based on initial conditions.
Right. Which
is an important thing to talk about with Bohmian mechanics. Maybe
I was just going to say, yeah.
The next thing we should move on to, because, so far we've pretty much said, like, okay, Bohmian mechanics is predictive. It says, we can know where this particle is going to go because we know Schrodinger's equation. We have this guiding equation. So that begs the question, okay, what about the Heisenberg uncertainty principle? How does that fall into the situation? Because we know that must be true, right?
Right. Yeah. And correct me if I'm wrong, but I believe it falls away in Bohmian mechanics. There is no uncertainty principle. It comes down to our inability to set up the same experiment with infinite precision.
Yeah, that's kind of like the way I saw it represented is we get the statistical nature of Bohmian mechanics arises from us not knowing the initial conditions precisely. So in the double slit experiment, we know if we knew where the particle was in the wave function exactly every single time as it passed through the slits, we would know where it was going to hit every single time.
Right.
But because we don't know exactly where it is, it goes off in different directions. So the best we can hope for is some sort of statistical interpretation or analysis of it.
Right. Exactly. Yeah. I mean, Bohmian mechanics is it's completely deterministic. Start with the initial conditions. They will tell you exactly what's going to happen for the rest of eternity. There's no collapsing of the wave function based on probabilities and stuff like that.
Yeah. So then it's just however, the way I kind of saw it and I interpreted it, the readings was just the more precise you could know where the particle is to start out with, the more precise you're going to know where it ends up. Because the position is absolute. There is a position of the particle where Heisenberg's uncertainty principle says, okay, position and speed can only be known to some degree. You can only know one more than the other. But Bohm says no, the position is absolute. We know that it has a position. We just don't know exactly what that position is. Right.
Yeah. I think the book I read with interviews, David Bohm has a quote, which I think is a pretty good one at summarizing his views on how things are working in science in general, in physics in particular. And he says, for thousands of years, people haven't asked themselves the right questions. In quantum theory, we're now asking a certain kind of question and we're getting a certain kind of answer. We may be putting ourselves into a trap by restricting ourselves to this way of thinking. So I think it's his knock on Copenhagen and how by subscribing to Copenhagen strictly, we're losing some other questions that might not be getting answered or might not even be getting asked by ignoring other interpretations.
Yeah, one of the videos that I saw had a quote from Bohm where I don't remember word for word, but it was, to paraphrase it, essentially it was, in developing Bohmian mechanics or pilot wave theory, he wasn't necessarily proposing this is the real way that the world is, but he wanted to show that there's another mathematically logical way to have all the same outcomes of quantum mechanics.
Right.
And so maybe we shouldn't limit ourselves to this one field or this one way of thinking about it.
Mm-hmm. Right. Yeah, it almost seems like he wasn't even a proponent of his own theory so much as a proponent of the idea of other theories existing or other interpretations existing, and they should be explored. And he just happened to come up with a pretty darn good one.
He took Du Bois and ran with it.
Right.
Right.
Yeah, that's right.
I mean, I don't know enough to, fully make a decision myself on like what I'd pick, but it seems it definitely feels nice in some regard.
It does. Yeah. And I mentioned the class that I took by the author of the book, which outlines 10 interpretations of quantum mechanics, 10 currently contending interpretations. And in class, we had to, after we read that section of the book, we came back to class the next time, and we had to go around and talk about which ones we felt were the most valid and why. And I was the only one that picked Bohm. I don't know why. I still can't tell you why I picked it, but just reading all the interpretations, it seemed like, that I could see that. That makes sense. Like, I see it.
Yeah, I mean, it just, it combines your natural intuition that there are particles out there,
mm-hmm.
and that with the, weirdness of quantum mechanics.
Right.
So it just generally feels nice, which isn't like a great reason for, that's not like a scientifically valid reason for choosing any theory over another theory. But yeah, it definitely like has some nice texture to it.
Right. And I think people actually knock Bohmian mechanics and knock Bohm himself, and he's had to fight back against people saying, you've made quantum mechanics less pretty because you've introduced a second equation on top of Schrodinger. Like, it was fine with just Schrodinger. Like, what's the problem? Like, and you've made it less elegant because you have a second equation now.
Right. Yeah. You had to introduce this other force. You made up a force.
So can I just read you the list of the 10 so people can get a taste?
Yeah. Let's hear them all. I only know of the three main ones.
Yeah. The three main ones. And when I took this class, it was the first time I'd ever heard of Bohm. And I went on to read more later. But Copenhagen, of course. There's Extreme Copenhagen, which was a son of Niels Bohr and another physicist also. It's Agat. I don't know how to say his name, but Aage Bohr. So Age Bohr, Niels Bohr's son. Their interpretation, it sounds crazy. Basically, particles don't exist. So all that exists is a source, what we would consider the source of the particles, and the detector, and anything in between. And that's it. So there's no particle in the double slit experiment that leaves the source and hits a screen. It's just the experiment, and that's it. So when you look at something, there are no photons that are going into your eye. It's just the source and your eye, and then the physical result of light. Like, that's it. So that's Extreme Copenhagen. I'm not going to go into as much detail on all of them because I don't understand all of them nearly enough to explain anything. Yeah, go ahead.
So that sounds like it just takes wave particle duality and just says wave.
It doesn't even do that. It's like there's nothing. Like it's just initial condition and result of experiment, and that's it. Like, that's all.
Okay. that really sounds like shut up and calculate.
Yeah, exactly. Let's say it's Extreme Copenhagen. Then decoherence, which, I mean, I can kind of explain this one, and this one kind of seems the most like, if you weren't trying that hard to think of something interesting, this would be the answer. It's just, it's basically, you can never get a perfectly isolated system, so all the weird quantum effects you'll never be able to observe anyway, like Schrodinger's cat, like all the weird stuff is basically washed away because there's always an interaction happening. You never have a perfectly isolated system. So why even ask these questions? Like, that's basically like EPR, Bell, like all that stuff just goes away because you can never actually do it, because you're always going to have an interaction with something. And that's kind of the attack on the experimental results of Bell's theorem, or the tests, the results of those tests, checking Bell's theorem, is that it's somehow entangled with this environment in a way that leads to just quantum mechanics can't necessarily be the whole story because you can never get a perfectly isolated system. So that's the decoherence, which is, it seems like a cop-out, but it also seems like kind of like, I could see it, I guess. Then there's many worlds interpretation, which you talked about earlier, Hugh Everett. Basically, the world splits every time something happens, and you get a new universe that's in this new, different world, and all those possibilities and probabilities that we saw in quantum mechanics are essentially, all of them are realized. It's just some are more likely than others, and you might end up in a universe where one of the odd ones happens, but who knows? The other possibilities do keep going on and existing without you. There's no way to check or to test that.
Yeah, that one just like, I mean, I don't know all the details, but just thinking about that blows my mind because real quick blows your mind. Yeah, because just the number of interactions that happen, that's going to cause like a wave function to collapse. So every time there's a collapse, essentially, you're going to get a large number of options that happen, splits.
Yeah, just forks over and over and over and over again. And every universe is existing. Anything that is possible happens. And then we get into Bohm, which we've been talking about, and pilot wave theory. And then there's a few that I don't know, like transactional. I don't know what that is. I guess it was, I don't know what transactional is. Then there's an Ithaca, which is coming from David Merman, who came up with the shut up and calculate, and also came up with the quick ways to discuss Bell's theorem that we talked about in the earlier episode. And quantum information interpretation. The wave function represents only information about possible measurements on a physical system. It's not to be identified with the actual physical system. It doesn't even describe the physical system under consideration. Okay, so I don't know what that means or how that works, but there's an interpretation called quantum information. And then there's quantum logic. And then there's GWR, which has three names, which you can probably guess their initials. And it's a modified Schrodinger's equation to make the wave function randomly collapse every now and then.
Huh. Is that trying to deal with the measurement problem? Well, no, because that'd be like a random collapse.
Yeah. Basically, the infrequent collapses wouldn't affect an interference experiment with isolated atoms. But if the atom is in contact with neighboring atoms, the atom would be entangled. So it seems like it's kind of like the decoherence in a way, but it's like somehow introducing it mathematically into the randomness of the collapse of the Schrodinger equation, or the wave function. So that's GRW. And then there's Penrose and Stapp is the last one. And then I think this gets into some heavy philosophy with
I think I've heard of the Penrose one. Yeah.
Those are the 10, all in order real quickly.
I have a few more things to say about Bohm, or Bohmian mechanics, I guess. Mm-hmm. That, so we kind of, I think we said this a little bit, but we kind of glossed over it to some degree. I wanted to get a little deeper on it, is, the measurement problem in Copenhagen interpretation versus the non-measurement problem in Bohmian mechanics. I think the double slit's kind of like the standard one that people go to, but the idea in Bohmian mechanics is, with using the double slit as an example, the particle goes through one slit or the other one, and when the wave function hits both slits, it creates an interference pattern. And so one of the wave packets that has the particle, or one of the wave packets that goes through, say the particle goes through the left slit, then the right slit is an empty wave packet.
Right.
And the two wave packets can still interfere with each other, even though it's empty. So then what's going to happen is the particle is going to follow some pattern and hit the screen. And at the screen, like now you have essentially a set of empty wave packets, and one of them is full where the particle is. In theory, there's some like those wave packets that are empty can still interfere with the wave packet that has the electron in it. It's just that now when it hits the screen, you have to take into account, the quantum, the wave function of the screen and that interaction. And it essentially kind of eliminates the probability of, I think it's along the lines of the decoherence, is once it's interacted with the detector, now the wave function's kind of, so washed out that the particle is here now. Like the future probability of the empty wave packets interacting is almost nothing at this point. And that's why there's no collapse anywhere. It's like it could happen, but now that we're taking into account the measurement device as part of this system.
That's interesting. I interpret it kind of differently. I think of the wave function going through both slits, and the particle goes through one of them following the wave function's guidance. And you ask, where did the particle hit on the screen? And you get an answer, and it's there. But I still, like, the wave function in my head still exists as the double slit pattern, like the standard, picture we have for the waves going through two slits. That pattern still exists. It's just that the particle has reached the screen, and there it is. But the wave function is still there. It's just that the particle has completed the journey, and its path has been shown to go exactly where we detected it.
Right, but I think kind of like one of the things I was reading is that there can be interference in the future between the other, like exactly what you said, except all the empty wave parts of the interference pattern could also still interact with the one that has the particle in it. But once you include the measurement device in the system, I think it kind of washes it out. Like there's some interaction between the measurement device that's going to eliminate the probability of any future interaction. And that's why then you kind of get this like localization. There's kind of one of the, I feel like that's the way it was described in the book that I read.
Yeah. I can see that.
And let me see really quick. Okay. This is a bit longer than, okay. Yeah. So here's how it's kind of described. In this book, and maybe this is a better way of saying, or maybe what I said wasn't exactly right, and this is what he's trying to say. So he talks about the Stern-Gerlach experiment, not the double slit. And so particle goes through, and it can either go up, down, or pass straight through. It's kind of the three options, and indicating spin up, spin down, or spin zero. In this case. And it says, okay, once the packet emerges from the B field, the magnetic field, the three components of the packet diverge along separate paths. After sufficient time has elapsed, the three emergent packets no longer overlap. Essentially, they have disjoint supports. And then, so I think there becomes a point when the particles or the wave functions no longer, they become disjoint from each other and they don't interact anymore. And that's why you don't have like this collapsing, because I think the idea is if I'm just kind of spitballing here. If the wave functions are still interacting to some degree, then the particle could move, because you don't know where it is in the wave packet. It could move from like one packet to another, or one crest to another crest. But at some point, the wave function is so spread out, or somehow has been interacted with, that you're not going to have this. You get disjoint wave packets essentially that aren't interacting with each other,
right?
And so you don't have this superposition possibility anymore.
I see.
Yeah, maybe I didn't say that very well.
I think I got it. I think I follow. Yeah, this is something I definitely want to read more about. And like I said, I was hoping to find an actual textbook that went through some of the math, or maybe even had like a problem you could solve. Practice using it. So you should try Holland's book, okay.
The Quantum Theory of Motion. And I think this is something that we can revisit. We're not, like I said, we're not experts in this. It was our first, pass at looking at this.
Right.
One of the other things that this book brought up is the classical limit. Did you read anything about that?
No.
So that tends to be another one of the issues, I guess, that people use when they talk about Copenhagen interpretation, especially when it comes to that versus the Bohmian mechanics. Sorry. And like within quantum, there's not a really well defined, or at least this author is saying there's not a really well defined like transition between quantum and classical. Like, and when I say classical, I mean like your typical everyday interactions that we're used to as human beings. And he talks about, like, he uses the example of general or special relativity, where you have the beta parameter, which is the velocity over the velocity of the object or whatever, right, over the speed of light, which is a unitless parameter.
Right.
And so we say, like, okay, as that parameter is much smaller than 1, that ratio is much smaller than 1, we get to standard, normal, everyday things that we see. We get Newtonian mechanics. And he says, in quantum, okay, so here, I'll just read this really quick. If quantum mechanics is to be a candidate for fundamental physical theory that replaces classical mechanics, then we would expect that there is a suitable limit in which the equations of quantum mechanics approach those of classical mechanics. So, just like special relativity goes to Newtonian mechanics, quantum should go to classical, is what he's saying. It is often claimed that the desired limit is h bar goes to 0. But h bar is not dimensionless constant, and it's not possible for us to set it equal to 0 because, h bar is a universal constant. And he says a more formal attempt at a classical limit is Ehrenfest's theorem. He goes on to say, essentially, it's not this easy, let this thing go to some value type of thing. But in Bohmian mechanics, you have the quantum potential, which is based on and I think particularly in Bohm's Bohmian mechanics, because he actually separated it into kind of a different, I've seen the equations expressed in his kind of style, and then also a more modern style, where he uses these R and S terms to represent the wave function that then decouples into 2 equations of R and S, but which are just arbitrary functions. But so he defines a quantum potential that's kind of based on the way the wave function is kind of laid out and spread out. But essentially, if you let and then once you express it in this form, you get out a force equation. You get dp dt, or force, is equal to negative the gradient of the potential plus the quantum potential, which looks just like a force, which is where the whole guiding thing comes from. So essentially, this author makes the argument, okay, well, you have the regular potential plus the quantum potential. Okay, well, take the ratio of that. So say you do the quantum potential to the regular potential, so 1 plus u over v. That's now a dimensionless quantity. If u goes to 0, you're not in the quantum realm anymore. Then you essentially get back regular classical mechanics. So he argues that there's this smooth transition between quantum and classical, or it's very easy to just find that limit.
Right.
Whereas the Copenhagen, it's a little more abstract.
Yeah. This speaks to the correspondence principle that Bohr was always strongly advocating for. But exactly what you were saying. There should be a connection. Basically, if an old theory of physics gives correct answers, the new theory of physics should give the same correct answers. You should be able to explain the same stuff using the new theory, which I don't know that Copenhagen actually has, an ability to. Yeah, you could, in theory, work out, the collision of billiard balls using quantum mechanics, but that'd be a ridiculous task.
Right.
There's no clear, like you're saying, there's no clear way to scale up quantum mechanics to take care of macroscopic physics.
Yeah, and with Bohmian mechanics, as soon as the quantum potential goes to 0, when you start dealing with macroscopic scales, right, then you just are right back at Newtonian mechanics, just instantaneously, which is kind of another
score one for Bohm.
Yeah. But I did read, I did see a couple of videos that were talking about issues with Bohmian mechanics. And I think the biggest one that I saw is its lack of non-relativistic applicability, I guess.
Yeah.
And that, with quantum, you have, your non-relativistic quantum, and then Dirac came up with the relativistic Schrödinger equation. And I think from there, somehow we end up at QFT, and that, I don't know. That's over my head.
Yeah.
So, and QFT is QFT is quantum field theory, very successful theory that is able to describe a whole lot of our world. But with Bohm, or in Bohmian mechanics, you can't get to quantum field theory right now. And so it really can't describe as much of the world as the Copenhagen interpretation can.
Right. Yeah. It's worth noting, though, that Bell was a proponent of Bohmian mechanics. I think we mentioned that in the last episode, but it's interesting to think about someone who's thinking about this pretty deeply, and he falls on the side of Bohmian mechanics.
Yeah, I want to read a few more, papers. Like I did see there have been attempts to, make a relativistic Bohmian mechanics, and apparently, like one of the other issues is that it makes reference to like Bohmian mechanics, as stated, has to have an absolute time, which like we know from special relativity, there isn't an absolute time. So
right.
So it's possible that this could be, like the start of a new quantum theory that could lead to something. But it sounds like in its current state, it's not quite as descriptive as the Copenhagen interpretation. Right. But like I don't mean that to mean that it should be shut down at all, right? I mean,
right. Yeah, it's interesting to think what if Bohmian mechanics was put forward first, and that's how we got our understanding of quantum mechanics, and then Copenhagen came later as another interpretation after everyone had learned Bohmian mechanics,
right? Or
many worlds, or any of the other interpretations. Like, what if they were the first ones?
Well, but Bohmian mechanics is like particularly interesting because it almost happened. Like, I mean, at the same time that they're coming up with the Copenhagen interpretation was, De Broglie was suggesting pilot wave theory.
We haven't really addressed why it's called Copenhagen. I mean, Bohr in Denmark basically is Copenhagen Physics Institute. I don't really know exactly the history, but it was kind of like, they all got together and said, this is quantum mechanics.
Yeah.
Here we are.
Yeah. What's that meeting has a name.
Solvay?
Yeah.
But I think that's in Belgium. I don't think that was in Denmark. The Solvay conference?
That's not just, I thought that was just the general name of the, because I thought they had a few of these meetings where they all got, all of those old physicists.
Over a few years they did, but it was always in Solvay. I'm pretty sure it was in Belgium. There's I was in Brussels and they had a big model statue of an atom. It's like enormous. I think it's in reference to that.
Oh, that's pretty cool.
The Solvay conference.
I did go to the Niels Bohr Institute for Physics in Copenhagen. I have a nice bust of his very bald, round head.
Yeah.
Outside.
I remember learning this stuff, or I guess getting into quantum mechanics and always struggling with the names because they're so friggin' similar. You have Bohr and then Bohm and then Born. Like all three of them were like huge in like early quantum stuff.
Yeah.
Like Born, we owe all of the like probabilistic interpretation of the wave function. That's Born. Like he came up with the postulate that like take the magnitude squared of psi. That's the probability of finding something.
Yeah. I feel like I still get it, all these guys confused.
Mm-hmm. Yeah. Bohr, Bohm, Born.
Yeah. Yeah. And then now we have Heisenberg is, the Heisenberg, the physics one. And then we also have this meth dealer that we consider for Heisenberg. And it gets so confusing.
Yeah. At least Schrodinger is pretty stand apart. There's no confusion with Schrodinger.
Yeah.
Except maybe how to spell it.
Yeah, that's definitely. Is there an umlaut or is there not?
Right.
What letter is it over? Yeah. I think I said this last talk, but last podcast, but I didn't get too into it. But essentially, Schrodinger's cat is Schrodinger trying to express the measurement problem of the Copenhagen interpretation.
Right. Exactly. Applied to macroscopic objects.
Yeah.
That's an easy way to see the problem, basically, is think about macroscopic objects, not just small quantum mechanical ones. And he found a way to think about them, to interrelate those two things with the decaying nucleus, which is completely quantum mechanical, leading to a dead or alive cat.
Right. Which is, he thought was just great, and he thought was a silly or a weird, not real thing.
Right.
But I don't know if you get this, but I feel like most people think Schrodinger's cat is a description of why quantum mechanics works. I feel like that's the popular interpretation, not popular, the layman, the non-physicist.
Mm-hmm.
So I'm trying to dispel that.
Okay. I don't know that I thought of it that way, but yeah, people think it's just wait, what is people think it's showing how quantum mechanics is correct.
Yeah, exactly. That it's like, or that you can really have a cat in like a superposition of dead and alive or something like that. That it's. I feel like most of my friends that don't know physics think it's a proponent for the Copenhagen. I mean, they don't know that the Copenhagen, but proponent for quantum mechanics, and not like an argument against.
Got it. Yeah, I can see that. So why don't we wrap up by just providing our sources, citing our sources?
Yeah.
The book that I was quoting Bohr from. So one of the books I checked out had an interview of a bunch of physicists. The title is The Ghost in the Atom, and it's edited by two people, Davies and Brown, and it's a collection of interviews with physicists, and one of them is Bohr, and it's a pretty old book. 1986. I guess it's not that old. And then the other book that I was referencing was the author's, the person who taught the quantum mechanics course that I took at grad school. Not as strict, quantum mechanics, rigorous physics problem sets, that kind of quantum mechanics course. But his book is called Quantum Enigma. It's by Bruce Rosenblum and Fred Kuttner. And if you go to UC Santa Cruz, Fred Kuttner's helping out with the undergraduate advanced lab, so you might have him as a teacher. And Bruce, I think, is still there. You can talk to Bruce and take his class. It's open to undergrads and grad students. And there's a whole bunch of other majors, like grad students of philosophy and a bunch of different disciplines that were taking the course with me. It was pretty interesting. But Quantum Enigma, Bruce Rosenblum. That's the one that had the big list of all the different interpretations. And the subtitle is called Physics Encounters Consciousness. And I've been deliberately avoiding the word consciousness through this last hour.
Yeah.
So, but the book does kind of go into that and talks about it. And, it's not as woo-woo as you think it would be. The book's actually good.
Yeah. And the one that I've been mainly referencing is, Quantum Mechanics by James T. Cushing. And then another, I feel like a pretty good summary for it. Let me find it online really quick. It's
while you're doing that, YouTube channel I was referencing was Looking Glass Universe. And she has a bunch of good videos on a whole bunch of different physics topics, mostly quantum mechanical topics. But yeah, she has a series on Bohmian mechanics in particular. Oh, and then the Veritasium video. Is this what quantum mechanics looks like?
I feel like we should just, have a standard Veritasium video.
Yeah.
Okay. The other website that I think has like a pretty good summary of all things Bohmian mechanics is the Stanford Encyclopedia of Philosophy. It's plato.stanford.edu. And if you just look up Bohmian mechanics in there, it's pretty good. It's not really, really long, but it has like a pretty good summary of it. I mean, if you just Google it, it's kind of like one of the first things. Another thing that we should mention too is maybe we can post a link to this or find a picture or something and put it in the show notes. But there's a really cool picture of the double slit experiment that you see everywhere when you look up Bohmian mechanics. That, like with Bohmian mechanics, you can predict the trajectory. If you know where the start of the particle is, you can predict where it's going to end up. Mm-hmm. And so there's this great picture of all the trajectories of these particles coming out of a double slit experiment. And you can see that the trajectories lead it to be clustered in these groupings, which end up being, the interference pattern. Yeah,
the bands on the screen. Yeah. Right. Cool.
Yeah, so that I thought that was a good source. And then the last, I mentioned this book a few times, but I didn't use it really, but I want to go more into it, is by Holland. It's called The Quantum Theory of Motion.
Cool. Well, that was good. We're so professional, citing our sources, giving references.
Yeah. And if you, the audience, know, any good papers on this or anything on the archive or something, send us a link. I'd like to read more about this. It's just,
yeah, for sure.
I actually didn't have like a great time finding sources. It wasn't, at least physical book sources.
Yeah. Yeah. Like I said, I never found a textbook, but yeah. Maybe just not in the public library.
Yeah. I found like there's a lot of things online. I just have to like be on UCSB's campus in order to access it.
Oh yeah. Right.
And I also just like, I'm old in my book values where I just like to have it so I can just like flip through it and go back and forth and stuff.
For this kind of stuff, that's definitely true. Like an ebook, like a collection of ebooks is not as valuable as, like, I just wanted to quickly reference and like look up several sources on this topic. I did the same thing for Bell's theorem when we were doing that the other episode. Yeah, it's much easier to have a collection of books to thumb through and kind of get a big overview of something quickly, much easier than websites. And well, websites kind of work because you can get a lot of sources real quick, but ebooks not nearly as good.
But yeah, I think the advantage that like a website has, maybe ebooks have this ability. I've just never really gotten into them. Is the find feature.
Oh,
it's
yeah,
just so nice.
Sure.
You're like, oh wait, what was that one thing? And you just Control F, and you're like,
that's true. Yeah, I was standing in the library in the area of this stuff and like pulled random books out and just went to the back and like looked for Bohm. And if it said it, I would go to those pages. And if it didn't, I put the book back. So that's my slow, Control F.
Yeah, that's exactly kind of what I did. I end up usually just like sitting on the floor and like, because they always have these books grouped together and just pulling out each one and flipping through it for a little while and then putting it back and doing the next one.
Yeah. Yep. It's weird. I went to the Quantum Enigma book because I knew that one. I went directly to it in the library thinking that's where all the other books were. It must have been, the number, it was in the correct place based on the number, but they're usually good about groupings. But it was completely surrounded by dinosaurs and fossils books.
That's weird.
And there's
that's
no
really
quantum
weird.
books anywhere else in that section. I was like, is it in the wrong place? I'm like, no, the number, it's right. It's exactly where it's supposed to be. But yeah, it's just, there's nothing else around it.
Cool. Well, yeah. So I hope I'm speaking for both of us. I think we might keep this up. Maybe this won't be every, maybe not the next episode and the next episode and the next episode we'll do this. But I think we should touch back on different interpretations of quantum mechanics, and
definitely
we could expand Bohmian mechanics too. But
yeah, I think I feel the most comfortable with many worlds and Everett interpretation as far as next options.
Oh, okay. Yeah. That'd be the next big one to read about before we go into, what's his name? I want to say Rosen. It's not Rosen. Who's the British guy?
Penrose?
Penrose. There we go.
Yeah.
Before we go into...
then we have to use the word consciousness.
Yeah.
It's unavoidable.
Yeah.
All right. Sounds good. Well, I will see you all in the next episode.
And, I think we should be saying subscribe.
Yeah.
Or...
thumbs up.
Yeah.
I don't know what it is. Like
share
on iTunes. Share.
Rate. Give us a review.
Yep.
And... and you can tweet me at @SPLEZAC.
Yep, I'm at Like Tortilla.
All right. Well, see you next time.
Yep. Take care.